Math students learn order of operations at an early age and can quickly look at infix expressions like 2 times 3 plus 14 minus 11 and know to add the 3 and 14 first because it is in parentheses. Then multiply 2 by 17 and finally subtract 11. A computer is not as naturally good at identifying those patterns, but given an expression in postfix notation, it will very quickly follow the same order of operations and also add, then multiply, then subtract. Computers prefer postfix, but humans don't know what it is. So in order to have computers do our arithmetic, we need them to convert from infix to postfix. The shunting yard algorithm makes this conversion nice and simple, with lots of flexibility to deal with even the weirdest math expression. The first thing we will do is divide the string into an array. Many cells will be just one character, but a number might have several digits. This algorithm is simple, at least for now. Just look for operators. Any other character gets added to the end of a string. When we hit an operator, we push that string to the array and then push the operator. For this example input, the only cell with multiple characters is the one with the number 16. Once we have divided the string fully, we iterate over this array to create the postfix array. We will need to use two arrays. One is the stack where we will temporarily store operators to get the order correct. The other is the final postfix array. Operands are immediately pushed to the postfix array. Operators are pushed to the stack if the stack is empty, or if the precedence of the operator is higher than the precedence of the last operator in the stack. If the operator has equal or lower precedence, we start moving operators from the end of the stack to the postfix array until the stack is empty or the precedence of the last operator in the stack is lower than the new operator. The computer would perform division first, then addition, then multiplication, then subtraction, and quickly yield the correct answer of -33. To help explain the algorithm, we will add a feature to walk through it step by step. To postfix 3 plus 16 divided by 4 minus 8 times 5, we first push the 3 to the postfix array. Then the addition is added to the empty stack for later. Then 16 is added to the postfix array. Division is added to the stack because it has higher precedence than addition. Then 4 is added to the postfix array. Now for subtraction, the precedence is lower than division, so we move division to the postfix array. Then addition becomes the last operation in the stack, and its precedence is the same as subtraction, so we move addition to the postfix array as well. Now the stack is empty, so we add subtraction to it. Add the 8. Multiplication has higher precedence than subtraction, so we add it to the stack. And finally add 5 to the postfix array. We are at the end of the infix array, so now we clear the stack starting from the end by moving each operation to the postfix array. Move multiplication and then subtraction. To handle parentheses, we need special rules. For an opening parenthesis, we simply add it to the stack. When we get to the closing parenthesis, we move operations from the end of the stack to the postfix array until an opening parenthesis is the final operation in the stack. Most operations are left associative, so 16 divided by 4 divided by 2 becomes 4 divided by 2 instead of 16 divided by 2 because the left division is performed first. However, exponentiation is right associative, so 16 raised to the 4th raised to the 2nd is actually 16 raised to the 16 because the rightmost exponentiation is performed first. Thus, when precedence is equal, exponentiation behaves differently than other operations. For most other functions, the input will be included within parentheses. We can simply add some strings with high precedence to our map, and the algorithm will work as expected. Factorial is weird because it occurs after the operand, so it is already in postfix notation. We don't want this operation to go to the stack at all. For max and min, we will add a comma operation that just keeps everything properly separated. Comparisons like equality have low precedence. Some operators are multiple characters, and we will handle those cases individually. I want to clean up the output so that the arrays are not quite so cluttered. To learn this algorithm, it helps to have an interactive tool that forces you to understand what to do at each step. You can push the element to the postfix array, push to the stack, move the last element in the stack to the postfix array, or delete the last element in the stack. When you have completed a step, move to the next token. It would be helpful to add some functionality to check your answer or undo actions at some point, but you can follow the link in the description to quiz yourself or make your own version of the quiz. Once expressions have been postfixed, it is really simple to write code that converts them into a variety of outputs. We can create LaTeX for displaying math, generate code in multiple languages, and/or just solve or simplify the arithmetic. I am working to make mathzeta.com achieve the goal of converting all sorts of math inputs to different outputs. If any of the code that flashed by was interesting to you, there are several links in the description. And go ahead and like, comment, and subscribe.